Next speaker, Dragos Horvath from the CNRS University of Strasbourg. Dragos is one of our most loyal attendees, I guess, to UGM, and he makes a fair amount of presentations with a lot of friendly criticism. And so he did his PhD at the Institut Pasteur in Lille, and was, according to his words, the corporate head and tail of molecular modeling at CEREP, and now is working for the CNRS.
Nice being here again, although this time things didn't go as planned. I would like to talk more about technical developments, but since we don't own our university cluster, there's more users than nodes. And I'll come back to discussing some science for a change. Sorry for the geeks in the room. So what's the problem? The problem is it's all your fault, guys. Because of this nice ChemAxon API, we were tricked into developing some quite interesting molecular descriptors, which are pH sensitive. They're chemically quite meaningful, and we kind of like them, and now we want to use them, and that's where our problem starts. So I'll just make a short flashback of what those descriptors used to be, although already mentioned those. So the first in the series were the fuzzy Pharmacophore triplets, where we used to count Pharmacophore triangles in molecules, but in a fuzzy manner, in the sense that, whoops, Bill Gates has cut the animation off. I knew something was going to happen today. In the sense that, well, if you have a molecular triangle, it will be matched on with respect to a set of basis triangles, and then the matching triangles will be incremented. The population level is not binary but fuzzy, and therefore the fingerprint is definitely not a binary one. Also, more recently we came, oh, that's a disaster. Now, how comes that I don't have any animation? Should have stuck to my own PC. Yeah, this one is not really understandable if everything comes in like this. So the idea here was that we were coloring atoms by Pharmacophore features, like in the triplet approach, but we do this in a pH-sensitive manner, in the sense that we enumerate all the microspecies here, the phenol and the phenolate. And then we are looking for the sequences of atoms colored by their Pharmacophore type, so acceptor, aromatic, donor. Bond types is also preserved, star being aromatic bond is a single bond. And then for each sequence appearing in these molecules, we increment the count by the population level. So we get a pH-sensitive fragment count with specific Pharmacophore definition. And so far so good. Yeah, there's even worse. This augmented atoms. So this is a kind of pH-dependent pipeline pilot-like circular fragment count based on the same principle. And I'm not going to go into further detail. These are published things now. Now, the problem is we want to do similarity searching with these huge descriptors, because there's a lot of possible fragments. The number of triplets is limited by birth to 4,900, which is already a respectable number. But if you go into circular fragments, you can have hundreds of thousands. So, and they're not binary, so it's no optimized Tanimoto, nothing. Oh. Of course, we are academics, so we wouldn't mind if we could have a coffee during the similarity searching. It's actually part of our job description. But, well, we are mortals nevertheless, and we'd like to know the answer before it all ends, you know. The big problem is that once you come out with a website and try to open these tools to the world, you can quickly be the victim of your own success if there's several jobs in parallel on our poor little machine. That would be the end of it. So, we came to Kohonen maps, and the idea is fairly simple. So a Kohonen map is basically a clustering exercise. It's a nonlinear mapping procedure which will take any fingerprint and will assign it to one of these neurons. So here the neurons are coded by size, by the number of molecules inhabiting them, and the neuron actually is represented by a code vector, which is a vector of the same dimension as the molecular descriptor, and the molecule will land in the neuron having the code vector closest to its own descriptor. So what you do is you take your query and locate it in a node, and then rather than caring about all the possible molecules, you'll focus your search on the candidates that reside on the same node or on neighboring nodes, because the idea of Kohonen mapping is to preserve the neighborhood, the topology of the initial chemical space, while nevertheless crunching it into a 2D stupid matrix. So we have tried to set this up, and there's a lot of acronyms and compound sets. So basically, we started with a set of 2,000 queries because we didn't want our results to depend on the peculiar query we have asked. We have taken many queries, and we have taken a sample database of 55,000 compounds, including PubChem, ZINC, whatever. There was no, we wanted it to be as random as possible, just to have a real-life study. And then for each one of these queries, you just run a classical unaided similarity searching and select the hits. And these become the official hits you'd like to find again once you go to the enhanced virtual screening mode. So there'll be at most 300 hits for each query, provided that their similarity is Tanimoto above 75% or Euclidean distance below 9. The cosmological constant 9 has been chosen in order to have roughly the same hit rates as you would get with Tanimoto. And then we have external sets for, we have training sets to build the maps, because you need some molecules to span this, rectangle in chemical space. And there's a large set and a small set to build the maps. And there's some external testing if I get there, because the coffee break is approaching. So the first issue is, okay, we build map, but what map? So we had to browse through a different, through a set of possible hypotheses. First question is, what do we use for training, the small or the large sets? What geometry, so how many neurons on X, how many neurons on Y? So from 8 by 6 up to 30 by 30, there's a lot of sampling to do. How long would you expect this map to need to be trained? So how many iterations? So we have entered the brute phase just to get it running, then a refinement stage. These were consistently performed all the time, and then we came to what we called hyper-refinement, and then we didn't know where to stop, so we explored several series of iteration numbers. So what do you see when you use this map for virtual screening? Well, the question is how large a neighborhood, how large a neuron box you would explore around your query. If your neuron radius is 0, then you will have to do the Tanimoto calculation only for the co-residence of the node in which the query was located. So you have a short computing time. This is the percentage of time with respect to the unaided virtual screening. But you also miss out on some hits which happen to be on other neurons than the one exactly on which the query resides. So this is a minimal one neuron screening, then you increase your radius to the neighboring neurons and to more and more and more. And the larger you get your screening zone, the more time it will take and the more hits you'll find. This curve will eventually end in the 1-1 corner. It can't go else. But now, interestingly, of course, the performance depends on the training efforts. And here you can see, obviously, the better curve is a curve that raises quickly. And you see that if you just do the brute training steps, so 1K, you don't get a very great response curve. You push further on with the 10,000 more iterations, it's getting better. And then, well, surprisingly, you see after 50,000 iterations, the benefit actually reaches a limit and then drops off. There is overfitting in the neural net in the Kohonen world, although Kohonen is said to be an unsupervised learning method. Well, you can overfit them nevertheless. 200,000 iterations would have been the yellow curve. It's actually a waste of time. So, the other surprise, this map was trained on the small data sets. This map was trained on the large data set. You don't need a large data set. Actually, too much learning gives a headache, even for artificial neural nets. And well, then we grew quantitative. We wanted to define an objective score, which is a compromise between the hit retrieval rates and the fraction of gained time to the squared, because we decided that we're in a hurry. And this is some plots just to keep things interesting. For example, if you take the quality criterion of maps trained on the extended data set versus the quality criterion of the same map but trained on the small set. And the red dots are the maps trained with 50,000 hyper-refinement versus maps trained at 100,000 hyper-refinement. So if you don't push the training too hard, and interestingly, the small set gives better results than the large set. If you do training extensively, or let's call it overtraining, then basically the green dots are equally spread to one or the other side of the diagonal. So if you push it hard, then the initial data set doesn't really seem to matter. But interestingly, the best results we got was the lazy solution. Small data sets, not so much training. And actually, so this sums it up. And we have, for example, so here you should have seen a nice map which doesn't show up. Colored, where the nodes were colored by the number of Lipinski violation, and you would have seen that the upper left corner is focusing on the molecules with Lipinski problems, whereas the southeast is Lipinski compliant, unlike in Europe, where the problems are rather in the southeast corner. But the map in itself is pretty coherent. And this is what gives if you push the directory of useful decoys, where now the nodes are colored by participation of different activity classes, and even nodes that are split between activity classes, you can see that this makes sense. Actually, pharmacophorically, I guess one was a kinase inhibitor, and I've forgotten the second. So they are from different classes, but pharmacophorically they are similar. So this is all based on pharmacophoric triplets, I've forgotten to say. So, okay, this is definitely something you cannot read. We have used this setup to do a library-to-library comparison. So we said our in-house library was actually the actual in-house library from our industrial partners, 160,000 compounds, and we screened 160,000 against 12,000 molecules from an external database, just in order to detect diversity holes and to see how quickly you can do this matchup. And it actually works, but you have to believe me or else try to see through this beautiful green color. Okay, so some conclusions, as I said. What started as a technical development exercise happened to become very interesting from a machine learning point of view, because we never expect when we started that we'll see overfitting artifacts, and notably that the smaller data set would lead to better maps than the larger. It's probably that too many molecules make the convergence difficult. So this has, however, a very practical consequence, is that unlike other virtual screening speed-up methods, because there's other methods using trees to structure your database in a certain fashion, you don't need to refit your SOM each time you add new molecules. So build a SOM, it will be there, then you can double the size of your database. Your SOM will probably still work very well. Too much fitting is detrimental, it's something we mentioned. Oh yeah, and then the other interesting fact is that SOM acceleration works. It's basically the same response. You get, you'll retrieve 90% of your hits in 10% of the time. And it doesn't really matter whether you do the virtual screening by Tanimoto or by Euclidean score. So the global neighborhood remains the same, and the map does it well. And then, well, needless to mention that this is not a fatal a no-go issue, because first of all, if you lose some virtual hits, you're probably not going to cry because of that. And if this really becomes an issue, you can just let this neuron box become larger and you find them again. So it's tunable a posteriori after installation. It's very easy to tune it up and down. And I think, what? Okay, this means that it's done. There's no more slides. So thanks for attention, questions, critics.
So I have a question. You did put a lot of effort in the number of iterations and testing this. Have you also considered using different map sizes?
Yes, yes. So this is implicitly that we are scanning short maps from very small, 8 by 6, so up to 30 by 30.
And after you have seen the final map, have you checked the U matrix, if there's really distinct clusters between your different pharmacophoric molecules? So the Euclidean distance between the values of the neurons? Could you see, like, this looks like what do you say? You get these sharp, distinct clusters if you look at the U matrix, and the neurons really have different values. So have you checked this or not?
Well, we had looked at various statistical indices, including these topographical indices, which tell you how distorted the local geometry is. But you know, there's so many. That was one of the problems. There's so many different points of view by which to judge the quality of the map that we actually took the opposite philosophical approach by saying, okay, in Q factor we trust. A good map is for us a map that enhances virtual screening, and then too bad if the topographic indices go astray. But there was no straight correlation between the Q index or, for example, quantization error and the classical things you're looking at when you do a Kohonen fit.
I wonder if you could give us a bit more idea about the feel of the kind of the how it's kind of implemented. My guess is that if you took a set of PDB ligands, you might hope they're kind of dropping out into the same node. Is that so? Have you? Did you actually test that?
PDB ligands, well, no, it's molecules that would drop into the same node would be, for example, small ligands. Those will definitely go into the same node, be it only because they might be too small to have populated triplets. Yes, you need well, some 10 heavy atoms to start having significant triplets in that combination. But otherwise, no, it's not a matter of, I'm sure there's a lot of PDB ligands in these data sets anyway, because we included marketed drugs and PubChem molecules and reference molecules that have been at least tested in literature, so all the QSAR data sets from literature are part of it. So, no, it's as the Dude picture showed, it's medicinally, chemically quite meaningful, so you'd expect, you see nice pharmacophore patterns in nodes coming up. But again, there's a virtual infinity of possible pharmacophore patterns and only a few hundred nodes. So at a certain point, an exotic molecule will end up in a location which doesn't make chemical sense. But that's not detrimental for virtual screening, because if you have a neighbor of it, it will be misplaced in the same way, if you want. So they'll find each other.
My name is Alexander Mendyk from Jagiellonian University, Krakow, Poland. That was perfect implementation of Kohonen-maps for the speed up of searching. Congratulations on your work. I wonder about this relationship between your size of data set and the results you have shown and the number of training epochs. How did you measure the training iteration of epoch? What was the epoch size?
Well,
the whole data set or predetermined number of records?
You mean number of?
Number of presentations of, how did you measure the number of iterations? As a number of presentations of the whole data set, or like each one record after each?
No, so the whole data set was presented to the map.
Okay. Okay.
And then what we did is go 1,000 iterations, then stop. And then, so the first, I don't know if you're familiar with the Kohonen package. First you do a random initialization of the neurons. Then you run 1,000 steps. You always take the latest map and push it through the next section. So that's why you will have a series of successive maps, one being the ancestor of the other. And we know that these effects are not due to an initial restart and re-randomizing of the procedure. The successive steps is as if you would do one continuous fitting and you stop from time to time and you look at the map.
Okay. Okay. Thank you. Thank you very much.